Hi everybody. Okay, we're back. We're on the fifth installment here of episode 7, where I'm going through different scenarios with weak acids, and I'm going to start throwing in a little bit of a comparison, strong acid to weak acid type of thing. How can you identify? So this video's I guess underlying question is up here on the board. Is this a strong acid solution or a weak acid solution? Like, how can you tell? Like, how do you identify it? Just based on some numerical values, okay? So, as per usual, I've got a problem up here on over my shoulder here. So the question is, and fairly straightforward question. So a 0.0010 molar solution of an unknown solute. Okay, so you've taken something, you've dumped it into water, and you've made it a solution of it so that it's 0.0010 molar. And there's a pH or a pOH. In this case, I put up pOH. So the pOH is 11.0 at 25 degrees Celsius. Okay, so let's go through a couple, and the questions are, is this an acid or a base? Is this weak or strong? So let's answer the first question. Is this an acid or a base? So the 25 degrees, first of all, is very important, because at 25 degrees, it means that we can use a bunch of things that we already know. It means we know we can use our K table if we need to, because all the values on here are at 25 degrees. So if we needed to do that, then we've got that. We also know that Kw at 25 degrees is 1.0 times 10 to the negative 14. As a result of that, we know that in distilled water, hydronium equals hydroxide because it's distilled, so they're equal to each other. It's neutral. Both of those are 1.0 times 10 to the negative 7 molar. We know that the pKw at 25 degrees is 14, which is important because pH plus pOH add up to 14 then, right? If you recall that one in the mathematical relationship in water's equilibrium. So, and that's kind of a critical piece here, because the question says, if you've got a pOH of 11, most of us don't think in the pOH scale. We think in the pH scale, right? That's how we were introduced to it. We were never taught, when in grade 10 or even grade 11, we were never taught what the pOH scale was. We could have been. I mean, we could have, all science around the world could have said, no, forget the pH scale. We're going with the pOH scale. So the pH scale and the pOH scale are related to each other, because the two values at 25 degrees always add up to 14. So as the pH goes down, what does the pOH do? Well, it's got to go up for it to still add up to 14, and then vice versa. So on the pH scale, 7 is neutral. On the pOH scale, 7 is also neutral. 7 plus 7 is 14. But if you go acidic on the pH scale, so meaning you go lower than 7, you go down to 5, you go down to 3, you go down to 2 and 1 and 0, and even into the negatives. As you go down, you're becoming more and more acidic. That's what we've learned. And as you go above 7, you're becoming more and more basic or alkaline. The pOH scale does the opposite. So as you're getting more and more acidic on the pOH scale, the number is going up and up and up and up. As you become more basic or alkaline on the pOH scale, the number goes down. So that concept, you've got to get your brain to think kind of the other way around. So when I give you a pOH value, your brain has to be thinking, don't think pOH is 11. Oh, that's got to be, it's got to be basic because it's greater than 7. No, it's backwards. It's the other way around. So a pOH of 11 means a pH of 14 minus 11, 3. So really what you have to do is you have to take that value right there and maybe put it into a reference frame that your brain sees really easily. Maybe you can see the pOH scale really easily. I know that in my own head, I have to take that value, and I mean, it happens pretty quickly, but that means a pH equal to 3.00. because the two numbers have to add up to 14. That's at 25 degrees. So pH of 3, okay, now my brain gets that really straightforward. That's below 7. It's acidic. Okay, so the answer to A is it's an acid because the pH is 3. Now, is it strong or is it weak? Okay, so we're either going to have a strong acid or we're going to have a weak acid. Well, understanding the definition of the two things is obviously very important. So knowing the distinction between strong and weak. So strong acids ionize 100%. If you've got molecules of a strong acid, 100% of them when you put them into water turn into hydronium. They all do it, 100%. So you can anticipate that if you've got X amount of acid and it's strong, you will end up with X amount of hydronium. And so those two numbers will be easily comparable. When you've got a weak acid and you've got X amount of acid molecules, you will have far less than X hydronium being produced because they go less than 100%. And it's that distinction that kind of gives away the answer to this question, whether or not it's strong or not. So what you need to do is you need to compare the acid concentration to the hydronium concentration. If they happen to be the same, then it was a strong acid because it went 100%. If the hydronium value is lower than the acid value, then that means it must have been weak and it didn't go 100%. So that's kind of the strategy of solving this type of a question, is to compare the two. Well, we don't have the hydronium concentration right off the bat. We have the acid concentration because it says that concentration of solution. No, it was unknown because I didn't want to give it away right away that it was an acid because I couldn't have asked A. So the solution is a 0.0010 molar solution of acid, some acid. We don't know the hydronium, but I do now know the fact that the pH is 3. So the hydronium concentration is done using our mathematical formula for how do you get the hydronium. So 10 to the power of negative pH. Plug in the value. And 10 to the power of negative 3 is going to be that. So that's what it is. Now, if you don't like it in scientific notation, just so you can see the visual representation here. So there's your hydronium, whether it's scientific notation or out of scientific notation, same number. So now what you're doing is you're comparing the acid concentration to the hydronium concentration. So here's the acid concentration. So the HA, remember I'm going to use the initial, I'm going to use HA as a generic form of an acid because I don't know what the acid is. I've determined it is an acid, but I don't know what the acid is. So I'm using HA. The HA initial equals that value, which happens to equal the hydronium. Therefore, the acid ionized 100% and is strong. So in this case, the acid is strong. If this number here, like let's say I gave you a different pH and you went through the exact same calculation, but this number right here came out something smaller, like quite a bit smaller, generally speaking, than 0.0010, then your conclusion would be, instead of equals to, right, you would have said less than. Okay, so the hydronium was much less than that value, and so therefore it would have ionized less than 100% and it would have been a weak acid. And that's kind of the critical element. Now that general concept applies to both acids and bases. So when we eventually get the bases, the exact same thing. Strong and weak has to do with percent ionization, not the pH. So some people might look at this pH of 3. Oh, that's like orange juice. Orange juice is 3. Well, it's not a strong acid. Well, pH has nothing to do with the strength. Ionization has to do with strength. So the fact that it's only a pH of 3 is because it was a pretty dilute solution to begin with. And so therefore it didn't make very much hydronium because it was dilute, not because it wasn't strong. Okay, so that's kind of a critical understanding between strong and weak. Okay, so the last little episode that we're going to have for these different these acid calculation things, the calculation of hydroxide in an acidic solution. And that'll be the next one. So I'll see you then.